This video is about enthalpy and how to calculate the heat using multiple versions and specifically Hess's Law. So you should really be able to define heat and energy and calculate the heat of a reaction using heat of formations, heat of bond energies, and Hess's Law by the end of the video. So the standard enthalpy of formation, or delta HF with a degree sign, is defined as an enthalpy change for the reaction in which 1 mole of a compound is made from its elements in their elemental forms at 1 atmosphere normal pressure and 25 degrees Celsius, which is about room temperature. Elements are 0 if the element is in a standard state. So in other words, if you have helium at that temperature and pressure and it's a gas, or like it should be, or calcium at that temperature and pressure and it's a solid, as it should be. If any of them are not the phase they should be at room temperature, then they are going to require heat to be given or taken out. The heat of a reaction with that degree symbol is the standard heat of a reaction at the same pressure, 1 atmosphere, and 25 degrees room temperature. And it's obtained by doing a products minus reactants, kind of like those bump diagrams, potential energy diagrams we've been doing that are products minus reactants. This is just doing that without the diagram. So you'll see big tables such as this. This is just one example where they give you multiple heats of reaction formation of the particles. You have one really big table like this in the back of your textbook, and it has every element and every compound. Notice on this list they didn't give elements because elements are 0 at room temperature and 1 atmosphere. And so this is just showing you how there's heats of formation for every single substance. They might be negative if it releases energy when it's formed, or they may be positive to form them. So this is how much energy is required or emitted when they're forming those compounds. To do a reaction, you just have to sum the products minus reactants. So in this reaction of C3H8 burning an oxygen to form CO2 and water, I'm expecting this to be an exothermic reaction because most burning reactions are, but we're going to confirm it by doing the products minus reactants. They also have to give you the values because you're not memorizing anything, but that the elements are 0. So if I start with the 3 CO2s, there are 3 CO2s in the products, so I'm going to do 3 times negative 393.5. I'm going to do the 4 waters in the products, 4 times negative 285.8. So notice I'm multiplying by how many there are. And I'm subtracting all the reactants out. And I do that by having brackets, all the reactant products minus all the reactants. So the reactants were C3H8. There's only one of them at 103.85. And notice it's on the table. You should know that there are 5 oxygens, each are 0. So I just showed it here for effect. But honestly, you don't have to write 5 zeros. When I put this in my calculator, I got negative 2,220 kilojoules per mole. I'm copying the units that are given to me in the table. That's really important. Copy those units. And notice it's already in kilojoules, so I'm not going to divide it by 1,000 to make it gigajoules or anything like that, unless you really wanted to. It's exothermic as predicted. So notice all elements are 0 if they're in their elemental phase at this room temperature, if they have that degree symbol. The units are kilojoules per mole. And this only tells us it's exothermic and might be favorable. We're going to come back to that. Here's another example. So again, it's products minus reactants. We're doing the Haber process, which is really common. So if you look up the ammonia is 46.1 on the table. It's negative 46.1. There's 2 of them, so we doubled it. And then the reactants are 0. So notice that this is only dependent on ammonia. So I wanted to show you one where it's really just doubling the products in this case because the reactants were both 0 because it is being formed from its elements, right? So they are not important. We're just figuring out what if it's 46.1 for one thing, how much is it for 2 is essentially what we're doing. But you can show it by products minus reactants. Another way you can get the heat of a reaction is by bond energy. We've done this before, but we're reviewing it, that each bond requires a certain amount of energy to break it. These are all breaking values in the black. The blue is just the length of the bond. And that can actually tell you something about breaking it. So you can see through like these ones, out of the single bonded halogen case, HF is the hardest to break because of those hydrogen bonds, and it's the shortest because of that. HI is the easiest to break because it has the least difference in electronegativity, so it's easy to break, and that's noticed as bond length is also long. So this is just a review. If you go through some of the double bonds and triple bonds might be near the bottom. Those ones are significantly higher because they're significantly shorter bonds because they're sharing more electrons, which make their nuclei closer together. right? So we want to make sure that we're picking at the right bonds from a big table like this. Most likely they're going to give you a condensed table. They'll give you some of the ones you need and a few extras just to see if you're paying attention. So here's how we would use the BARF rule. Anything that you're breaking, you have to add together, and then anything you're forming, you have to negate, because BARF stood for breaking absorbs, and you release energy when you form a bond. So the problem with these questions is, if you were given heat values, you did products minus reactants. But if you're given bond energies, you're doing reactants minus products. See how that's a little confusing, and we'll review that in class. So CH4 is breaking 4 CH bonds. Remember, if you draw it out, there's a bond to 4H 4 times. So 4 times 4, 13. And we're also breaking 4 FF bonds, which are 154 each. So 4 CHs and 4 FFs. I'm going to subtract out the ones that we're forming. We're forming CF4, so that happens 4 times of F on each side of the carbon, 4E5 times 4. And if it's a coefficient, we're forming 4 HF bonds. The HF was 565. Notice the formation ones are negated. Is it common that they're all going to get 4? No. It just happened in this question that we had tetrahedral particles, so that's why all the bonds are 4. You have to draw these out to figure out what you're breaking and forming. At the end of the day, this reaction was negative 193 kilojoules per mole. Notice again, I'm copying the units from the chart in case they give you different units. And it's an exothermic reaction, which means it's probably favorable, but not necessarily. The third way we can find the heat of a reaction is Hess's Law. The heat is well known for many reactions, like the one we just did, and it's inconvenient to measure the heat for every reaction that we're interested in and in publishing that, because the charts get just as long as the heat charts of formation. So we can estimate it by using other heat values that are published, and the way we do that is if a reaction is carried on a series of steps, we just kind of simply sum all their energy changes into one step. We did something like this earlier in the year when we talked about all the ways that we can add like ionization energies, electron affinities, and all the steps bond energies together. We had added all those together to get the lattice energy. This is the exact same idea. Right? We're just doing it again as a review. So for one example, they gave you water is going from solid to liquid and it requires 6.01 kilojoules to do that because solids have little energy and liquids have more. And then the CH4 methane is burned in oxygen to form CO2 and water. Water is liquid in this phase, and that gives off 890 kilojoules for every time it goes through. What we want to know is if we kept that reaction the same but we changed the water to solid, what would that energy be? So it would CH4 is noticed to be the same except for it has a 2 coefficient. The oxygen is the same except for it has twice as much coefficient. CO2 is the same again 2. The water is the same except for 2. So that means this whole entire reaction needs to be doubled. If we double the reaction to match, we need to double the heat. Additionally, the water has changed phase. So instead of it being liquid water, I want it to be solid water. In order to do that, I need to reverse the first reaction so that the liquid's on the opposite side, so it will cancel. I'll also need to double it so it completely cancels with a 2 in coefficient. So if I rewrote them, we're multiplying the first equation by 2 so that matches the coefficients. Therefore, the heat's multiplied by 2. And we're reversing and doubling the first equation. So that way that the water's 4 H2O liquids will, quadrupling, will match the 4 H2O liquids on the left. They will cancel and we can just sum the heats. So I'm going to sum 2 times 890 and my negative 4 times 601. We still see that it's still exothermic reaction because it's happening twice as much, and the fact that you're making a solid helps it be even more negative. At this point, you should be able to find the heat of a reaction either using heat of formations, bond energies, or Hess's Law.